Welcome, everybody. Today, Jakub Rydval from Technical University Vienna, Austria, is going to talk about the polynomial hierarchy and omega-categorical CSPs. Please, Jakub.
Yes, thank you for this nice introduction. Yes, as the title says, polynomial hierarchy and omega-categorical CSPs. I want to talk about some ongoing project that I have with Santiago Guzman Pro from TU Dresden. And yeah, to not make it too dry, I prepared some story in the beginning so that you can also enjoy some of that. Okay, so since I guess there's a very general audience here, I will start the story with an introduction, a short introduction to CSPs. So what is a CSP, constraint satisfaction problem? It's a computational decision problem parameterized by a finite, let's call it tau. And in this problem, we're given as an instance a finite tau structure A, at least according to the homomorphism perspective on CSPs. And then the question is whether there exists a homomorphism from A to B. And a standard example of a CSP with a finite domain of a finite relational structure is tree coloring. And this is actually the CSP of the complete graph on 3 vertices. Okay, so what is the standard definition of the tree coloring problem? We're asking whether there exists a vertex coloring of a given undirected graph with 3 colors, let's call them red, green, and blue, which avoids all monochromatic edges. And this can be seen as a CSP of the complete graph on 3 vertices, because the only thing that is not forbidden in a complete graph on 3 vertices or that is forbidden actually are loops, right? So we cannot map two adjacent vertices to the same vertex, and this gives you a direct translation between the CSP definition and the standard, let's say, combinatorial definition. Now, just for illustration, if we have this Peterson graph here, then a tree coloring also corresponds to a homomorphism from the Peterson graph to the complete graph on 3 vertices. And now, what somehow made this the study of constraint satisfaction problems prominent was the so-called algebraic approach. And I will now cover the algebraic approach just very briefly on 2 slides. And the algebraic approach relies on a particular algebraic invariant, which is the notion of a polymorphism of a relational structure. So if we have a relational structure B, then a polymorphism is an operation on the base set of this relational structure of a finite arity. And this operation should have the property that if we take any relation of our structure, any fixed one, and we pick k tuples out of this relation and we plug them in to this operation f component-wise, then the output should again be a tuple in the relation. And then the set pol B is the set of all polymorphism of our structure. And this actually forms an algebraic structure. We could see elements, we could see these operations, these polymorphisms as elements of an algebraic structure whose signature will consist of some projections, and we will have a composition operation, and then it would form a clone, which somehow generalizes monoids. And now let me give you some examples. So an example that is always present is projection operation. So the operation that takes k many arguments and outputs always a fixed one is always a polymorphism of any structure. And then binary minimum operation is a polymorphism of, for example, this structure here down below, where the domain is just a 2-element set 0, 1. Then we have a weak linear order, and we have 2 unary relations for 0 and 1. And there was this initial observation, which a part of it goes back to Jevons 98, and part of it is much older. And the observation is that if we have 2 relational structures over the same domain, such that the polymorphisms of the structure A are contained polymorphisms of B, which one could interpret as B having more symmetries than A, then the constraint satisfaction problem parameterized by B reduces in a logarithmic space to the constraint satisfaction problem of A. And this holds for finite structures. So this was somehow the first level of the algebraic approach, where people have observed that the complexity of CSPs of finite relational structures is completely encoded in their polymorphisms. The second level was to actually not look at polymorphisms as concrete operations, but to look at some identities that hold in these polymorphisms. And now I just want to briefly cover minor conditions, which are particular sets of identities or equations. So a minor condition is just a set of equations of the following form. We have terms which are not nested, right, with some operation symbols f and g, and then we can have variables as whichever we want, and then the equality must hold between these two terms. And how to interpret it for a polymorphism clone. A polymorphism clone satisfies such a minor condition if we can assign polymorphisms to these symbols f and g, such that for all possible evaluations of these variables, we will have an equality. And now I want to just introduce a shortcut for particular preservation of satisfiability of minor conditions. I will say that pol A maps to pol B. This means now for us in this talk that for every finite minor condition that is satisfied in the polymorphism clone of A, this minor condition also has to be satisfied in the polymorphism clone of B. And now I will just give you an example, and you have to trust me. So if we start with this structure B1 that we've already seen on the previous slide, and we expand it by one more relation, it's a binary relation, just contains these three tuples, then there is actually this minor condition preserving map from polymorphisms of B1 to polymorphisms of B2, which I'll tell you later what it means for the complexity of the CSPs. But actually, the polymorphisms of B1 are not contained in the polymorphisms of B2. And so this can be seen, for example, if we take the minimum operation, it's a polymorphism of the structure B1, but it's not a polymorphism of the structure B2. But now, just to give a concrete example of a minor condition that is satisfied in the polymorphisms of B1, we could take commutativity, for example, which is witnessed by the minimum operation. Then this commutativity condition also has to be satisfied in the polymorphisms of B2, regardless of the fact that minimum operation is not a polymorphism. So in the Wonderland of Reflections paper, Barto, Opperschall, and Pinsker have formulated the following very elegant property of these maps between polymorphism clones that preserves minor conditions. Namely, if we have a map from pol A to pol B, then the CSP of B reduces in log space to CSP of A, which is actually just a generalization of what we saw on previous slide on the first level of the algebraic approach. And they also observed that if we take a finite structure, then whenever we have a map that preserves minor conditions from the polymorphism of A to just the set of all projection maps, then the CSP of A is hard for, one could say, purely algebraic reasons. And then the final somehow the culmination of the algebraic approach was the dichotomy theorem of Bulatov and Juk, who after decades of research have put all the puzzle together, and they proved that also the converse actually holds, that for finite structures, whenever we don't have this minor condition preserving map to projections, then the CSP is tractable, which means that this algebraic reason for hardness that comes in this item 2 is actually the sole reason for hardness for finite domain CSPs. And this is a dichotomy theorem because it says that for finite domain CSPs, there are no intermediate cases of complexity between NP hardness and polynomial tile tractability. So finite domain CSPs somehow constitute a large fragment of NP, which do not have any, which does not have any NP intermediate problems. Okay.
Could you repeat the definition of this minor condition of this implic this arrow?
So let's say it is a weakening, algebraically it will be a weakening of a clone homomorphism, right? So it should somehow commute with composition operations, but these compositions cannot be arbitrary. We can only plug in projections and a single operation.
Can you say what it means? Pol A satisfies sigma means what?
You were asking about pol A satisfying sigma, what this means.
In the definition, yes. Right.
So pol A satisfying sigma means that we can take this set of equations and we can assign polymorphisms to every single symbol in this set of equations. By this I mean the operation symbols F and G, right?
Yes.
And then in the structure A, for all possible inputs for the variables, the equation will be satisfied. It will be an actual equality between the images of the operations, right? So, for example, minimum is a witness for commutativity as a minor condition, and it just would say f of xy equals f of yx. Yeah.
Okay, thank you.
Okay. Yeah. Now let me get to omega-categorical CSPs. So I'm still somehow in the story part of my talk. So omega-categorical CSPs, what is omega-categoricity? And what is omega-categorical CSP? So omega-categorical CSP is the CSP of a finite structure or a countable structure that is omega-categorical. And the definition I want to give here is that for every k, the action of the automorphism group of the structure on the kth power of the domain of the structure should only have finitely many orbits, right? So the structure is not necessarily finite. It can have a countable domain, but it is somehow approximately finite in that there are not infinitely many orbits for linearity. And the canonical example here is of an omega-categorical CSP would be the CSP of the ordered rational numbers. And this structure is omega-categorical because if we look at two tuples P and Q of the same arity, then they are in the same orbit if and only if they somehow induce the same weak linear ordering on their entries, right? If they're ordered in the same way, we can always map one to another with an automorphism. And since there are only finitely many such configurations for every given arity, this shows that the structure is omega-categorical. So what is interesting about omega-categorical CSPs? The interest in them started with a paper of Boris and Eshetril from 2006, who have showed that actually this fact that the complexity of finite domain CSPs is completely encoded in their polymorphisms, it translates to omega-categorical CSPs. So if we have two structures that are omega-categorical and have the same domain, then whenever the polymorphisms of A are contained in polymorphisms of B, we have a log space reduction. It's the same result as before. And then in this Wonderland of Reflections paper of Bartol and Pinsker, 2015, they also looked at omega-categorical CSPs, and they proved that whenever the polymorphisms of A admit a minor condition preserving map to projections, and here one has to add some additional assumptions on the continuity of this map, so it would have to be uniformly continuous, whatever that means. Then whenever this happens, the CSP of A must be NP hard. So there's a reason, an algebraic reason for hardness, which covers many cases. And actually before this paper was published, Bodersky and Pinsker made a dichotomy conjecture, which, if proved, would actually generalize the dichotomy theorem of Bulatov and Juk. And what they conjecture is that for a specific subclass of omega-categorical structures, I will not give you the proper definition. It's like this redux of finitely bounded homogeneous structures. Whenever polymorphisms of A do not admit a minor condition-preserving map to projection, that would be uniformly continuous, then the CSP of A should be in P. So somehow an analog, a generalization of the dichotomy theorem of Bulatov and Juk. So what makes this conjecture great for me personally? I mean, of course, I'm interested in this area, but it's a conjecture that has survived for very long. It has been confirmed for infinitely many cases. And it actually gives a framework for studying some very natural combinatorial problems, for so-called forbidden color pattern problems. I will not give you a definition. I will just give you an example that is quite similar to tree coloring that we've seen before. Okay, so vertex, no monochromatic triangle, which asks whether there exists a vertex coloring of a given undirected graph with just two colors here, blue and red, but you could choose more colors, such that this coloring avoids monochromatic triangles, right? So this question. Before we had monochromatic edges, now we have monochromatic triangles. This is actually a CSP of an omega-categorical structure. It is not a CSP of any finite structure. And just as an extra fact, it actually also falls into this dichotomy conjecture. So it also satisfies this mysterious condition RFPH. And now just a visual example. We have this star graph. And this is actually a positive instance of this non-monochromatic triangle, right? We want to color vertices with two colors such that we avoid monochromatic triangles. This problem, similarly as tree coloring, is actually NP hard. Okay. And now, last but not least, the study of this conjecture motivates the algebraic study of omega-categorical CSPs. So by that I mean study of omega-categorical structures, and it motivates extensions of algebraic results that have successfully led to the resolution of the dichotomy theorem of Bulatov and Juk, which was before that a conjecture. So there is a line of research that is trying to generalize algebraic results from finite structures to omega-categorical structures. And now I am more than an algebraist. I'm a logician and a complexity theorist. So for me, the following question is interesting. How complex are actually omega-categorical CSPs without any restrictions, right? Because there is this line of study of omega-categorical CSPs without any additional restrictions or with very mild restrictions. So it would be interesting to know like how complicated these problems actually get if we don't put any fancy assumptions. Okay, and this is where I somehow start the main part of what I want to talk about. So in this now relatively old paper of Bodersky and Eshetril, they showed that despite the fact that the complexity of an omega-categorical CSP is always encoded in the polymorphisms, there actually exist undecidable omega-categorical CSPs. And this proof is quite non-constructive. They just show that they observe that there are uncountably many different omega-categorical CSPs, while there are only countably many algorithms. So of course, not all omega-categorical CSPs can be solved by an algorithm, right? But what I find more interesting is some of the subsequent results. So there is another paper 2 years later by Bodersky and Grohe, and they have some more constructive proof, like constructions of hard omega-categorical CSPs. And to present this result, I first want to give you a definition. So now we want to look at complexity classes which rely on the oracle model. So A to B is the class of all problems which are in A, right? If runtime A, if we allow an algorithm with such a runtime access to a solver for B, to an algorithm from B. And this definition is used to define the levels of polynomial hierarchy. So polynomial hierarchy was in the title of my talk. So what is it? Polynomial hierarchy is a hierarchy of complexity classes above NP and its complement co-NP. So just to be on the safe side, NP is the class of all problems that are solved in polynomial time by a non-deterministic Turing machine, which just means that if we identify solution to a problem, then if we guess a solution, then we can verify it efficiently in polynomial time. And now co-NP is the complement, which means those are the problems where if we have a negative instance and we have a certificate for that it's negative, we can verify the certificate efficiently in polynomial time. And now by these powers, we can define higher levels of the polynomial hierarchy, right? So for example, the second, and there are always the left-hand side and the right-hand side, or so there are sigma classes and pi classes. And for example, sigma 2 would be NP to co-NP, right? And pi 2 would be co-NP to NP. This definition sounds quite abstract, but there are very natural complete problems for these classes. So problems that are within the classes and that are also as hard as any other problem in the class. So a natural problem here is satisfiability of so-called quantified Boolean formulas. So a quantified Boolean formula is a formula which does not have any signature. We're just working with variables which evaluate as 0 and 1, and we allow connectives, the standard connectives like conjunction, disjunction, and negation. And then we allow a quantifier prefix which tells us how to quantify over these variables, right? So for all x1 exists x2 such that some Boolean expression should be satisfied. And now if we restrict the quantifier prefix to n blocks of alternations, such that the prefix starts with a for all quantifier and has length n, then this would be a natural problem for pi p n. So I see that here I have index I, this should be an n. So satisfiability of such formulas is a natural complete problem for pi p n. And in this paper by Boris and Grohe, 2008, they first one result that is somewhat linked to this polynomial hierarchy, but I just want to start with it now. They show that there is a co-NP intermediate omega-categorical CSP. So for sure, if one would try to extend the dichotomy theorem from finite domain CSPs to just purely omega-categorical CSPs and switch it from the NP side to the co-NP, then this would not be possible because there are some problems which are neither in polynomial time nor they are co-NP hard. And they showed, so now I'm coming back to the polynomial hierarchy, that this is maybe a bit more difficult to digest. For all cases where there exists a co-NP to C complete language or problem, there will also exist a co-NP to C complete omega-categorical CSP. And now this condition would work for all possible complexity classes C that you can imagine. But for us to be more reasonable, to have something concrete, we can think of these pi levels of the polynomial hierarchy, right? So for example, co-NP to NP and so on. So in particular, for every n greater than or equal to 1, there exists a pi pn complete omega-categorical CSP. Now, much later, more than 10 years, a set of authors have looked at how the evolving algebraic approach to omega-categorical CSPs interacts with these results, and they were actually able to improve it by adding this condition that within the infinite domain CSP dichotomy conjecture should represent the tractable cases, right? So what they showed that for all these, let's say pi pn complete omega categorical CSPs, one can additionally achieve that the polymorphisms will not have a uniformly continuous minor condition preserving map to projections. And this somehow shows that like on the side above QNP of the polynomial hierarchy, the algebraic approach, like just looking at identity satisfied by polymorphisms, cannot tell us much about the complexity of the problems. And now I found it also, me and Santiago, we both found it a bit curious what is happening with the classes above NP, right? So now I'm talking about NP itself, but also let's say NP to co-NP. Now, for sure, we would not want a result like, for example, this first item in Bodesky-Gruyer 2008 for NP, right? Like we don't want to see an NP intermediate omega categorical CSP. If there is one, it would still not mean anything necessarily from the conjecture, but it would tell us something about the strength of the algebraic approach, just restricted to omega categorical structures. But what could happen is that we would be able, for example, to reprove the number 2 result for classes of the form NP2C. And in order to do this, now comes the technical part, is we need to actually understand the old proof strategy, right? So how did Bodesky and Gruyer construct this, the CSPs? Okay. Because omega categorical structures, they have to be represented somehow, right? One has to construct them in using some model theory. So in their proof, yes.
Can I ask about these omega categorical structures?
Yes.
Typically, when you construct them, typically they will be computable or recursively enumerable.
These structures, they will be computable in that they have a representation, right? Like we will start with the QNP complete language, and then we construct a class of structures which encodes this language, and this would be the representation of the omega categorical CSP. Somehow, I don't think you can have a better representation than that.
I don't understand what the connection between a language and the structure is. Is like a problem.
It will be like you have a finite alphabet and you will have a subset of sigma star. So whenever there is a language that is co-NP2C complete, right?
Yes.
Then there will also be an omega categorical CSP, a computational decision problem, a CSP of an omega categorical structure, which has the same complexity. And how we get this
is computable or not?
It is computable. It is computable because it is represented by the language. You will see on the next slide.
Okay. Thank you.
Yes. So we need to understand the old proof strategy, right? We start with language L. As I said, it's a subset of sigma star, and we assume that it's co-NP2C complete for some C. And now we define a particular signature. And this signature consists of 2 unary symbols I and T and a binary symbol N. To check on which slide I am, 18, okay. Binary symbol N, and then we also have binary symbols for all possible letters of the alphabet. This is our signature, and now we define a class of structures from the language. So this class will be all possible finite structures over this signature tau, which have the property that they do not admit a homomorphic image from any finite structure F, which is of the following form. First, maybe I will actually start with the second item. So the symbol N should interpret as the inequality. and this structure should encode a word from the complement of our language L, right? And the encoding of the word would be just by a sequence that starts with I and then follows somehow the word and ends with T. And this will actually be the representation of our omega-categorical CSP. This is how you represent the structure. Now you have to prove that there exists a structure which is omega-categorical and has this class as a CSP, which is what now I will just very briefly go over. Okay, so for this class that we defined, we have some closure properties. First, this class is closed under unions. How can we see this? Union, I just mean if we have two structures that overlap on some part, and then we just take the structure which has as its domain the union of the two domains, and relations are just unions of relations of both structures. Now, I claim that if we know that none of these forbidden structures from above map to B1 and B, and this is actually due to a very simple fact, namely that this relation N interprets as the inequality, right? It's like a complete graph. And now if we take the union of two structures, then for any pair of vertices which come from one structure and from another structure, but they're not in the intersection, there will actually not be any N relation between them, so we cannot map F into the union unless we already map it to one of the two structures. So it's a cheap trick. This class is also closed under inverse homomorphisms. I would say this is even easier to see. So if we know that F does not map to B and we have a homomorphism from A to B, then of course F does not map to A, right? And these two notions will come back later again. Now, actually, just by having these two, yes?
In the second line, what does the satisfaction symbol mean? Are the words part of the language of the signature? The words are part of the signature?
So the words, so the signature is like this, right? It has two unary symbols, I and T, N, and then there's a binary symbol for every letter. Okay. So by this, maybe I should have been less sloppy. I should have write it out. This means I of X and X arrow A1 to let's say X1, and then X1 arrow A2 to X2, and so on and so on. So there should be a chain.
This is the okay. I see. Sorry. Yeah.
Okay. Yeah. Okay, so since this class is closed under unions, this gives us the so-called amalgamation property, and then we have a Frasse class, and by Frasse's theorem, there will be an omega-categorical structure that is described, whose substructures are described by the class, and since we're closed under inverse homomorphisms, actually the class already describes the CSP of this structure. So this is how you get how the original proof works. Now, what about complexity, right? Because now I just told you how to get the omega-categorical CSP, but I haven't told you anything about the complexity. If you think about what is the CSP of D, what does it do, right? The CSP of D is the problem of checking whether in every n-clique of a given instance, it is true that the words that are encoded in this n-clique do not come from the complement of the language, right? So yeah, we need to somehow check every possible n-clique, every possible complete graph in the relation n, and then whenever we see an encoding of a word, we check whether if it's in L, then we say yes. If it's in complement, then we say no, because that's forbidden. And from this definition of the CSP, you can see that L actually reduces in polynomial time to CSP of D, simply because we can take any possible word from sigma star, we encode it over a clique, and then the question whether it maps to D answers whether it's contained in the language or not. Right, so this gives us hardness for the complexity class that we started with, coen P2C. And in the other direction, CSP of D reduces under coen P many one reductions to L. And since classes of the form coNP to C are closed under such reductions, we actually also get the upper bound. So this is how you show that the CSP is coNP to C complete. Okay. Now there is a problem with NP to C, and namely the problem is that we cannot afford to encode the complement of our language along n cliques, and this is bad because we used n cliques to get to have this closure property of being closed under unions, which allowed us to use Frasis theorem. But at the same time, if we forbid encodings of words on n cliques, then we cannot really hope for anything better than hardness for coNP to C. Right, so we have to select an alternative approach, and this is what we did, me and Santiago. So we realized that in the literature there is the following sufficient condition of Borowski, Knoer, and Rudolph of 2021. It tells us that whenever we have a class definable in monadic second-order logic, so it's just a fragment of second-order logic where every quantified second-order variable, every quantified relation has to be unary, then if K is closed under inverse homomorphisms, and disjoint unions, so not unions but disjoint unions, then there will be an omega-categorical structure D such that the class is the CSP of this structure. So just writing down definition of this closure property. So closure under inverse homomorphism we've seen before, right? If we have a homomorphism from A to B and B is in our class, then A should also be in our class. Homomorphisms is the other way around. If we have A in K and A maps to B, then B should be in K. And disjoint unions, it's simply that we take isomorphic copies of our structures so that the domains are disjoint, and then such a structure must be in our class. And what we showed, so there's not a preprint yet, but there will be one, is that for every n greater than or equal to, there exists a sigma Pn complete omega categorical CSP. So sigma Pn is the side of the polynomial hierarchy that's above NP. So NP2 co-NP and so on. All right, so how did we do this? And now I want to somehow split the proof into two parts. There will be like a conceptual part and there will be an ad hoc part. So the conceptual part is a certain preservation lemma. So we say that a second order sentence is normalized if it's in so-called a pre-next normal form. So this just means that we have a sequence of second order quantifiers, then we have first order quantifiers, and then we have a quantifier free part. And now we want that this quantifier free part is in conjunctive normal form. So it should be a conjunction of disjunctions of literals. So it's like a very polished way to present a second order sentence. Then assuming that we have a normalized sentence, then we say that it's positive if atoms from the signature, the underlying signature tau, can only appear positively. So they should not be negated, right? We take a look at this conjunctive normal form, and every clause, if there is a tau literal, then it should be positive. And now a second property, which we call existential guardedness, is a bit more complicated. So we have a normalized sentence, and for every clause phi in the quantifier free part, which is in CNF, right? Whenever we see a universal first order variable in a given clause, then there should be a negative literal containing this variable, such that S is an existentially quantified second order variable. So this somehow means that if you look at evaluation of second order sentences as a game between an existential and a universal player, this means that the existential player has control over the universal first order variables. Now under this notion, we realized that it gives us sufficient and necessary condition for preservation under injective homomorphisms, right? So second order sentence is preserved under injective homomorphisms if and only if it is equivalent to an existentially guarded positive sentence. And this gives us an idea like what sort of sentences to look at if we want to have preservation under homomorphism at all, but so far it's just injective. To give you, so for convenience, in our results, we also actually close this notion under conjunctions and disjunctions internally. So by that I mean that if we have two sentences where we have some quantification over S1 and all the way to Sn, these will be some second order variables, right? And we have a similar sentence with the same prefix, and we know that they're both existentially guarded or positive, then also this internal conjunction and disjunction should be existentially guarded and positive. So we close the definition of existential guardedness and positivity under this rule. Now let me give you an example. So we have a property of structures in a relation in a signature consisting of a single binary relation symbol, and the property is that there exists a non-empty subset S of the domain where this relation E is strongly connected. And if you think about it, this is just a fancy way of saying that E contains a directed cycle, but here we only use unary symbol. So this is symbol unary second order variables. So this is a monadic second order sentence. And now in order to check that it's closed under injective homomorphisms, we just need to go through all its constituents and check that every universal first order variable is guarded by an existential second order predicate. And here we only need to look at the last clause, and this is indeed the case, right? There are two variables that are universal, x and y, and they are guarded by this existentially quantified second order variable S. There is an obvious dualization of this concept, and that would be negativity, right? We want that tau atoms only appear negatively, and existential guardedness will be dualized to for all restriction. Now you really just need to invert everything, so I will just spell it out. So for every minimal hitting set of literals for all clauses, and for every existential first order variable that we see in this hitting set, there should exist a positive literal S of some variables, including X, in this hitting set, such that S is universally quantified. So this somehow gives the universal player control over where existential variables existential first order variables need to be evaluated. And then the dual lemma says that we have preservation under inverse injective homomorphisms if and only if we're equivalent to a for all restricted negative sentence. So this is the conceptual part of our proof. Now the question is, what about surjective homomorphisms and disjoint unions? And for this, we actually need to apply some ad hoc construction. And this will be the CSP hammer, and then hopefully the general idea of the proof will also become clear. So we can prove that whenever we have a for all restricted negative MSO monadic second order sentence phi, which has a quantifier prefix containing at least one universal second order quantifier, then there exists a monadic second order sentence with the same prefix, and we will denote the sentence phi CSP, such that we actually have everything, almost everything that we wanted, right? We have preservation under inverse homomorphisms, we have preservation under disjoint unions, and we have reduction from the original sentence to this new sentence. So we start with the sentence phi, which is for restricted negative. This ensures that it's preserved under inverse injective homomorphisms, and after applying this construction phi CSP, we have preservation under all possible inverse homomorphisms. So how does this work? Right, we start with such a sentence phi, and we identify the first position in the second order quantifier prefix where there is a universally quantified second order variable. And in this new sentence phi CSP, we will actually have one new unary second order variable and one new binary symbol, right? And I specifically chose n for the name of the symbol to somehow link it to the previous construction above QNP. And the sentence phi CSP looks as follows. We squeeze in a universal quantification over U in between the last existential second order quantifier in the first part of the existential prefix and between the first universal quantified second order variable. And then we replace this quantifier or this first order sentence psi that constitutes the first order part of phi with a modified version of it. And this modified version, it consists of the original sentence psi, which still remains there, but now we have two additional conditions. The first condition, this psi not edge, checks whether there is a pair of vertices which do not have an edge in n. And if this happens to be the case, then the sentence phi CSP is automatically true. And this sentence psi not loop, ensures that there is no loop in the relation n. And then what we additionally do is we restrict this expression syntactically to the predicate u, right? It's a general construction from logic where you just relativize the sentence to u so that existential variables have to be evaluated in u, and the universal evaluation of universal variables only matters in u. Okay, so just to keep in mind what the construction looks like. Now we want to prove these three properties that I promised. So for the first property, which is preservation under inverse homomorphisms, we first decompose homomorphism into a surjective and injective part, right? Every homomorphism can be first viewed as something surjective and then injective. Now, since we syntactically restrict to u, we keep this Fourier restricted negativity, this property that we had for the original sentence phi. But since we added this non-edge and non-loop, it's not really clear if it stays. But since we added the restriction to u, well, we still have it. And this gives us preservation under inverse injective homomorphisms. And now for the preservation under inverse surjective homomorphisms, we actually need an ad hoc argument. And this ad hoc argument is simply whenever we have a surjective homomorphism that somehow contracts two variables, two elements into one element, then since loops are forbidden, and if we start with a structure which is a model of our sentence, then it cannot have a loop, which means that between these two variables that are contracted, there cannot be an edge. And in this case, this first sentence, non-edge, just says yes. It says this is a valid structure. So this preservation under inverse surjective homomorphisms is achieved by a bit of a cheating, but nevertheless, this is fine for us. And for preservation under disjoint unions, we do a similar ad hoc argument, right? If we have a disjoint union of two models, then of course between these two models there cannot be any n edges. And then whenever we're evaluating the first order part of this phi CSP sentence, which is relativized to u, then it just matters whether u sees only elements from one structure, or if it sees some overlap, and if in the case of an overlap, it would immediately say yes because of this not edge sentence. And then we can show that there is a polynomial time reduction from satisfiability of phi to satisfiability of phi CSP, and this reduction just expands a structure with inequality. This is very similar to what was happening before in this old proof. And the reason is that if we just take a structure in this original signature tau and then we expand it by inequality for the symbol n, then this non-edge and non-loop become irrelevant, and verifying phi CSP is just the same as verifying phi. And for this, we need this Forel restrictedness condition, but maybe I will not go through this now. But it's important that we have this Forel restrictedness condition because it allows us to actually push this quantification over U through the first part of the existential prefix, and this means that in the end, this sentence phi CSP will have the same second order prefix as the sentence phi that we started with. And now using this first preservation lemma, right, this conceptual part and the ad hoc construction, we can prove our result. And we prove it simply by starting with some complete problems for this levels of the polynomial hierarchy, and these problems will be the satisfiability of quantified Boolean formulas with particular prefix. Since this theorem is now only formulated for n greater than or equal to or 2, there will always be at least one universal quantifier in this prefix, and in this case, we can just transform this QBF with the prefix Q1 to Qn into a MSO sentence with the same prefix that will contain a universal quantifier. We just need to ensure that it's Forel restricted negative, and that QBFs with this prefix actually reduce in polynomial time to satisfiability of phi. Okay, and now we just apply the CSP hammer. This is the ad hoc construction, and this will actually give us a sentence which has all the preservation properties that we would want, and it has the right complexity because we keep the quantifier prefix. And now we just apply the theorem of Podolsky, Knoll, and Rudolph to actually get omega-categorical structures D, whose complexity is the desired one that we wanted. So I hope that I managed to make it somewhat transparent. Like I have some more slides, but of course there's no time for it. Why I decided to give you this conceptual ideas was that I don't have to explain everything in an ad hoc manner for this formula because it's too long. So thank you.
Thank you.